Either of there's one.
I have some goodies in my pocket. Would you like some? I think about caramel apple stuff. Well, what happened was, in one of my education classes last night, we were playing a Jeopardy game on Dr. Seuss. Every question, I got to see how to so. And it was on Dr. Seuss.
I don't know what Dr. Seuss is. I know it was a real movie. It was right. So close. That's all I know about that.
Some people didn't even know that last night. I was like, good. I'm on fire. I answered 15 questions correctly. I knew the answers to some of them that went on, but I didn't answer the combat.
I hate that.
Quick. On 5? Yeah, you don't have to.
Half 2 is 1 to 2 to 5. Half 2 is 2 to 5.
Like 3 p.m. to 5 p.m.? That's not a good time. No, that's what the mark out for in class is 30 to 3:30 to, I lied, 2 to 3:50.
Not like, no, it's still 5. Because I can't right afterwards. I have stats, and I have 30 minutes break, and I have calc.
Stats is easy though.
I'm sad.
I promise.
You should take the 10, because I can't just go to stats.
I mean, you like to know you can't get it. Right.
Maybe I'll just do it anyway and do really well. Why do I have this not for stats? I can just do those things.
I don't know, I had to pick that first.
And then she goes over stats. Oh, I'm done. I quit.
Okay, if you've got this class down, that class will be like the bottom. I don't know how that happened. It should not have happened.
I doesn't have really only.
Good thing. It's fine. Doesn't take it.
Cool.
But you do need to do it. And promise if you don't do it, you're not going to do it.
I will do it.
I'm telling you.
I've already taken out.
Because sometimes she'll surprise you with going around the person getting it.
I have read it very I do that all the time.
Are you sure you don't want to find a weapon?
Maybe, but I gotta
I think if I go back and get mine, all that, so it'll be me. I will not touch Matt 10-foot pole.
I want to get laser, psychology, chemistry, a lot more things.
So what are you going to do?
Minor than that.
I mean, well, all of it. Like what you're going.
Chemistry and psychology. 3 years. Where I earned 4 or 5 of. But
Like Spencer.
surprise.
I thought about doing that.
I
Compromise. What compromise? Needs to like watch.
She told me.
It's like a childhood project.
I didn't know.
That's good. I know there's a movie called really long.
It's fun. I don't know what it is.
Pretty long.
It's like, oh wait, 11.
My
No, it's the other day.
get this done. And that. Which are, they're not. Then I'm going to go back there and find out. It's really hard. Her. And eventually I'll
I
go
think
back there.
3. I don't have one.
I'm gonna get a doctor.
I can't.
It'll put you on the center.
I told you. I'm not getting a doctor. Did you?
I think you
Did you
just
get
like
like?
a special doctor.
Did you get like the same?
I didn't even hear that.
I did it.
I'll pay off my like $2,000. I did that, and I just simplified it. Like I don't know if she wanted it or not, so I okay.
She's got like an
So do you guys
might be handy. Sometimes you hear about
suggest taking
like math teachers' kids are worse than math.
Not unless it's required.
Well, I just,
It's not gonna be required.
it's a math credit and it's a big time on class. I mean, getting the transfers up or something like that. Back it up. Just, I was thinking.
I'm thinking of next
That's
semester.
just that's
3,000?
I'm not taking history.
I thought you already took it. Just you 1,000?
Yeah, I'm taking it up next semester. But after class. Like 23. Oh, it's her and Alan. I thought it was
Yeah.
you two. I pick up my.
Oh, finally.
It's just 12.
Like, that's been so long.
Yeah.
Alright, so we're doing our video.
Yes. And I was thinking.
Yeah.
For our
jazz. So you're reading.
So what's up?
but I'm really angry.
Yeah, because you're not in class. We're just.
I know.
We're doing like an interview type thing. Chapter. I'm not gonna say that. I brought note cards so we can have. Write on it to refer to.
Yeah. I was also considering
Yeah. Oh, okay. Yeah. Isn't that what you're doing? It's this man. Yes, it is. Are you with Allie? She's the PowerPoint. Yeah, so you have to do a PowerPoint. Yeah. So you guys have any friends? Where is it? Not our gallery. I was wondering, I already signed up. You really don't have to do anything. Well, like, I signed up for it. Oh, you did? You do?
Okay, Megan. Here. Elsa.
Here.
Morgan.
Here.
Allison. Katie.
Here.
Leah.
Here.
Catherine.
Here.
Curtis.
Here.
Okay. All right. Now, today, we're going to continue chapter 10, relations. So, on Monday, we discussed the definition of relations, and I gave you some examples of different relations. So 10.2 is going to talk about the properties of relations. Chapter 10, 10.2. So As you can see from the title, we have three properties. One is called reflexivity, symmetry, and transitivity. Okay. First of all, there are different ways that we can do this check whether a relation has a certain property. So first of all, I will give you an overview of these three properties using real-life examples. So what does reflexivity? It's like you and yourself. So you look at yourself in the mirror. So it's sort of like that type. Remember when we talk about property, it's going to be related, right? So we say somebody is related to somebody. But remember, when we say related, it doesn't have to be by blood. It could be anything, by age, by major, by any kind of thing you want to define. So here I'm going to give you some sort of like real-life examples. Suppose we're talking about people, maybe our students, or in general. Well, I guess we could talk about students in our class. So previously, when we defined the relation, we have A times B, and we say X from A is related to a Y from B, if and only if there's some kind of relation defined. So let's recall the examples we did last time. You could have say X is less than Y, or X minus Y is even. These are some examples we did. I guess I can just rewrite it here. So possibly you could have defined as X minus Y is even. That is a relation. Or you could have, let's define another one, where X is related to Y. I'm going to use L this time. If and only if X is less than Y. That's another example we did. Thinking about real-life examples, well, I may define X is related to Y if X is younger than Y. So as an age, instead of less than, right? So I can say X is younger than Y. Or X's age is the same as Y's age. I could define equal one. So let me give you another one. Number 3. So X is related to Y, and this time I guess I can use maybe H. X is related to Y if and only if X is equal to Y, or you can say X has the same age as Y. All right, so now we can talk about these three properties. First one, reflexive. What does it mean? It means, well, when we say a person is related to another person or a number is related to another number, we never say these two have to be different. Although we use different letters, X, Y, but X, Y represent numbers or people, anything. They could, excuse me, X and Y could be equal, could be the same thing. So you could have discussed the 1 and 1. Is 1 related to 1? Is 2 related to 2? So it's possible. So whenever we talk about, let me give you just a make-up example. Suppose I'm talking about A. Whenever you talk about this, you have to know, okay, the first person or the first number, where does it come from? Where does this person come from? If I say X and Y are people, so I'm going to just kind of make up some people's names. Say maybe A is the set A. We have people. I guess we say maybe Austin, Elena. Well, I guess kind of mixed with this. Maybe use lowercase. So Austin, Elena, and James.
and I could maybe come up with some more, like Curtis and different, maybe Morgan. Okay, so we have five people here. B, I can use the same. And previously we had different A's and B's, but A and B could be the same. I'm going to make them the same. That. Now when we define X, so how do I define that? I define it as X is related to Y if and only if X has the same age as Y. X is as old as Y. So now, well, I guess I'm just gonna put some age here. So let's say Austin is 20, Elena is 19, and James is say 19, and Curtis is 21, and Morgan say is 18. So I'm just gonna put random numbers here, and now that's what I want you to determine is which people are related. So who is related to who? By looking at the relation here. So how do we determine that? Don't forget when we do this, you also have to check you and yourself. Okay. So look, is Austin related to Austin? So X is from A, Y is from B, but X, Y could be the same person. So let's check. Is Austin related to Austin? Yes, right? Why? What's my definition? I put X equals Y, but you can think of it as age. So X has the same age as Y. It's the same age as Y. If we think of this as the real life example. But in this case, yes, A is related to A. So I can put A and A, so that A is rated. And what else? Is A related to Austin related to Elena? No, because 20 is not equal to 19, right? So no. What about Austin and James? No. Austin, by looking at that, we know it's not gonna, Austin is not related to anybody else, right? Because you don't have anybody who is age 20. So we check it. You have to check every single one, but because this one is actually a little quick. And what about Elena? So we're going to start with Elena. Is Elena related to Austin? No, it's 19 and 20. Is Elena related to Elena? Yes, because she's 20 and she's 20, so you should put an E and an E there. Next one we check, is Elena related to James? Yes, right? Both are 19. We got E and J. And that's all we have, right? Okay. Now let's start with James. James and Austin, no. James and Elena, yes. James and James, yes. And nothing else. Now, Curtis, as you can see, Curtis is not going to be related to anybody else because he's 21, right? But he's going to be related to himself. And the same for Morgan. So that's all the related pairs we can find, right? Any question about this? No. So the one which property is called reflexive? If you look, the reflexive property is, did you notice that everybody is related to him or herself, right? Because of the relation defined. So Austin is related to Austin, Elena is related to Elena, James is related to James, Curtis is related to Curtis, and Morgan is related to Morgan. So if you have that, if you satisfy that, anybody is related to himself or herself, we say this property is reflexive. Okay, so I'm going to put because I use the H to represent this relation, so I can write down H and put all of them in the curly brackets. So previously I asked you to do Cartesian Cartesian product. On the second exam we had a question like that. So this is how we use it now. And so pretty much when you have somebody related to somebody, it's gonna be like an ordered pair, okay, or a product of two sets. So these, because this relation, by looking at the pairs, I found out everybody is related to themselves. So I say this relation is reflexive. Again, how do you memorize this? What kind of relation relation is reflexive. You and yourself, anybody and himself or herself. It's like I said, you and maybe like your image in the mirror, right? So you can think of it as your image in the mirror. So you and yourself. You're not comparing yourself to anybody else. So when you check reflexive, I'm going to write down the definition of reflexive. So what is a reflexive property? The first property called a relation. A relation is defined. Let me first write down this because I have to use this property 3 times because we have 3 properties. So a relation is defined on the set on A times A. So usually when we talk about these 3 properties, we make sure these 2 sets are the same. We talk about A and A the same. So A and B are actually the same thing. So we don't have different ones. And so we have first one, reflexive property. So this relation R is reflexive. R is reflexive if and only if for every element in A, every element in A, X is related to X. So in words, this written in words will be every, in my example, every person in here, for every person in here, he or she is related to himself or herself. So that's what it is. Okay. When you look at the set, the other way to write X related to X or X related to X, you can put the other way to write it is like what we see here. What do you mean A common? A common, that means A is related to A. But I use the H because I call this relation H. In general, we use R, but if I already used R, because I used R in the first example, I can't use R again because it's a different relation. That's why I picked the H. But over here, the other way to write it could be XX is in there. So that's the other way. Usually, I think we memorize it this way, but you should know that's the same thing. Okay, so is reflexive property clear? So if you understand this, I want you to go back to check that 2 relations we discussed on Monday, and tell me whether each one is reflexive or not. So let's look at the first one. Is the first relation reflexive? What do we check? Here we're not checking persons anymore. We're checking numbers. X and Y are numbers. So what do we check? Remember, reflexive is you and yourself. So here we're talking about a number. So it's the number and this number itself. Does the number and this number itself satisfy this condition here? James? Did you say it satisfies the reflexive property? And can you explain why? It does satisfy this first relation is reflexive, but can you explain why this is reflexive? Does anybody else know? How's it? Can you say it a little louder? Yes, that's right, exactly. Okay. All right, so whenever you want to check whether relation given, so this will always be given. They will tell you how the relation is defined, either, by you have to do something to check whether this 2 numbers are related. So in this case, whether 2 numbers are related, it depends on the difference of these 2 numbers is even or not. If it is even, then you say related. If not even, then you say they're not related. But how is reflexive defined? The reflexive property says any number, in this case x is number, any number should be related to itself, right? So you may say, well, I don't know what the number this is. You didn't tell me what A is, what B is. It really doesn't matter now. I can tell you A is all real numbers. So if I tell you A and B are both real number set, real number, all real numbers, and all real numbers. And so you pick x, any real number. The second number will still be x because reflexive is checking x and x. Look, over here, x represents the first number. The second number y is also x because reflexive just always check you and yourself. So when you go back to look at the real life example, you have to check you with yourself and everybody else, right? So when you only check you and yourself, when you are checking this, you and yourself, you and yourself, you and yourself, you and yourself, this is checking whether it's reflexive. So when I do that, I don't have to worry about anybody else. When I check reflexive property, I check every number and itself. So when I plug in x and x, what's x minus x? X will be x, y will also be x because you're checking the number and the number itself. So x is going to be the same. And x minus x is equal to 0. Is 0 an even number? Yes. So apparently it works on every number. I don't have to check every single one now. I can check 1. Well, 1 is 1 related to 1? Of course, because 1 minus 1 is even, right? Is 2 related to 2? Yes. 2 minus 2 is 0, which is even. Is square root of 2 related to square root of 2? Yes. Square root of 2 minus square root of 2 is even. 0, because it's 0. So you don't really have to check every single one, pick numbers, because we know any number you pick, whether it's 1 or 2 or square root of 2, or even 7.9 or 1/2, negative 1/2, when you subtract them, you're always going to get 0. So this works on any number you can think of, right? X minus x is always 0. So if this works, every number x is related to itself, you will say it is reflexive. Okay, make sense? All right, so this is, how do we write down the answer? Usually they want you to write down an explanation. So this is what you have to do. So how do I know the first one is reflexive? What you need to write down is, so the relation defined is A times B, A times A. Where A here is a real number set, equals the real number set, all real numbers. How do we know it's reflexive? Because for any x from A, x minus x is equal to 0, which is even, And by the definition of the first relation, if a number minus another number is even, we say they're related. Well, x minus x is 0 is even, so we say x is related to x. But usually we don't use words. We just put, instead of saying x is related to x, we just put an x related to x. So you can just use that instead of the words. Okay, and that's exactly the definition of reflexive property. For any number in there, that number is related to itself. And we say, so it's the property R, the relation R is reflexive. So that's what explanation you have to write down. So this is kind of like a proof, but it's very easy. All you have to write down is like one sentence. Most of the questions are not just one sentence we do. So just say, okay, y is x related to x because x minus x is equal to 0 is even. Okay, any question about this? Now let's look at the second one. Is the second relation, this was the first example we did. Is the second one reflexive? No. Can I tell why it's not? Because can a number x be less than itself x? No, it's not possible, right? So that's why It actually doesn't work on any number, and that's why it's not reflexive. So the second one we defined, the second relation here, why this is not reflexive. Not reflexive. So you can write down the second example because you can say for any x, but what if you can find one counterexample that will work? So there exists a number such that x is not less than x. Because for reflexive, every number has to be related to itself. But if you find one is not related to itself, that will you can say it's not reflexive. So what does this mean? X is not less than x, which means x is not related to x. I use the L here, so I'm going to use L. It's not related to x, which means the L relation, that's the example I'm doing, the second one, is not reflexive. Okay. So here I give you pretty much like 3 examples. 2 of them are reflexive, 1 of them is not. So you can think about real life examples. Say marriage relation. You define a person, X is related to a person Y. If X is related to X is married to Y, think about that relation. Is that a reflexive relation? So if I define X is related to Y, if and only if X is married to Y, and check the definition. Is the marriage relation reflexive?
No,
Is it reflexive? No. Why not?
because you can't be married to yourself.
That's right. Okay. So remember, when you check reflexive, these two will become the same person or same number, right? So usually, normally, we wouldn't consider you married to yourself, right? So that would be not reflexive. What about a major? What about a major? If we define it as major, I guess I can call it M2. Major relation. X has the same major as Y. I think that's one of the homework questions. Has the same major as Y. Is it reflexive? Yes or no? Yes, right? Okay. Because you would consider you and yourself. You must have the same major as yourself, right? Same. So it will be reflexive. The other one, I guess, we can. Yeah, I think that's. Hopefully, this gives you an idea what a reflexive property is. So we're going to move on to the next one, which is reflexive. So you do have to memorize that definition there. I give you, real life examples to help you memorize that definition. You and yourself, the number and itself. Check whether these two, the same number or same person, meet the definition. Now, symmetry. So what's symmetry? Let's go back to that H example we had at the beginning here. So symmetry, what's symmetry? Symmetry is talking about two people, usually different, because we already checked the same. If you and yourself, we already checked. So now usually when you check the symmetry, you only need to check the different ones. So for example, E and J are different. J and E are different. Elena is related to James because Elena has the same age as James. James is related to Elena because James also has the same age as Elena. So this is called symmetry. If I tell you, okay, Elena is related to James, and then you also see James, if you can conclude James is also related to Elena, then we say this property is symmetric. But not every property is like that. Let me write down again the definition. So what is, this one is also symmetric. And I'm going to write down the definition back there. The second one, a relation is symmetric. What's the definition? The definition says, now this time, look in the reflexive property, we only have one person or one number, x. And we compare x and x. But for symmetric property, you must have two, x and y. Normally they're different. And if x is related to y, then you have to determine, you have to verify or check whether y is related to x. If this is true, then you say it's symmetric. If it's not true, then it's not symmetric. So the age relation we just looked at is symmetric because I found that Elena is related to James. And then I also found James is related to Elena. So which satisfies the definition? The definition says if one person X is related to another person Y, then you must have the second person Y related to the first person X. So pretty much what do you check? After you switch them, they should still be related. But not every relation will satisfy that. So if you look at the second one we just did here, the second example that I gave you, and we also discussed this on Monday, is this one symmetric? The first number, if the first number is smaller than the second, can we conclude the second will also be smaller than the first? No, right? It's not. The second one will be greater. We know the second one will be greater than the first, right? If x is less than y, after you switch then, can you still say y is less than x? No, right? Y should be greater than x. You cannot keep that relation anymore. In that case, you say it's not symmetric. How do you explain that? You can pretty much you have to say y is not going to be less than x. X is less than y, but y is not less than x. So that's why your explanation will be for not reflexive, not symmetric. What about the first one? Is the first relation x minus y is even symmetric? Remember you're doing switch. You switch x and y. No? Yes or no? Okay, now let's go over the definition one more time. The definition says symmetric. If I tell you x is related to y, can you tell me y is also related to x? So you already know if condition. So we talked about conditional statement at the beginning of the semester. So this is like saying, in this case, if x is related to y, what does that mean when we say x related to y for the first relation here? X minus y is even, right? So it's kind of like saying, okay, I'm telling you x is minus y is even. Can you tell me, can you determine whether y minus x is even? You're going to switch x and y, right? So if you know x minus y is even, can you determine whether y minus x is even? Yes or no? That uses yes, right? Simple property of algebra for numbers. Think about it. Any number, say 7 minus 5 equals, it's even, right? When you switch then, do you still get an even number? Yes, right? But by the way, I'm just giving you an example to show you why this even and even, why this is true. When you do the proof, don't use this as a proof, just like we had before. So how would I prove this is symmetric? So I'm going to go back to, okay, let's check that symmetric property on this example. So on this case, x minus y is even. For any x and y from the real number set, from A, whatever A is, so real number set. If A is a real number set, real numbers here. if x minus y is even, then I can prove y minus x is even. By the way, you cannot pick numbers like I did, 7 minus 5, 5 minus 7. Well, this is a question, should be a very easy problem now, because we did this, I guess, before the first exam, probably, on the first exam and the second exam. How do you prove it? If you know a number is even, how do you describe it? How do you describe an even number? It's going to be 2k, right? Okay, so if I tell you x minus y is even, you can write x minus y as 2k. And then, how do you get y minus x from x minus y? It's opposite, right? So how do you get opposite? Multiply by -1 both sides. So I can multiply the left by -1, the right by -1. So I'm going to get -1 times x, negative x. -1 times negative y. Negative times negative is positive, plus positive y. But I'm going to move y on the front to match that. On the right-hand side, I'm going to leave that 2 there and multiply k times -1. What's k times -1? Negative k. And look, can you tell whether y minus x is even here? That's even because we said if you can factor 2 from expression, that has to be even, and that's an integer. So apparently that's even. So this is the form of proof, and using the definition of even number we learned before. Or if you think this is obvious, because y minus x is always the opposite of x minus y. If x minus y is even, opposite, you put a minus in front of it, should also be even. And from here you can tell. If a number is even, you're just going to change k to negative k. It's still going to be even. You still have that 2 there. So if you want to say that, because y minus x is always the opposite of x minus y, so it should also be even. You can also use sentences to explain instead of using that. It should also work. But this is very straightforward from the definition. Okay. So here you can say, so the relation is, this relation R is symmetric. And now I want you to think about the other real-life example that I gave you. What about the marriage relation? Is that symmetric or not?
Yes.
Is that symmetric? Yes, right? Because if I tell you x is married to y, you can conclude what? Y is married to x, right? That's for sure, okay? So marriage relation, yes, it's symmetric. What about a major relation? Is that symmetric? Yes, right? If x has the same major as y, y must have the same major as x, so it's also symmetric. These are this is the second property. I do want to point out in the past there was some confusion about this. The second one. The second property says if x is x is related to y, then you have to have y related to x at the same time in order to say it's symmetric. But what if x is not related to y? Then you don't have to have y related to x either. So if you go back to, let's go back to the age relation we talked about at the beginning. This one we did say it's symmetric. It's a little different from reflexive. Reflexive, you got to make sure everybody is related to himself or herself. So if, say, somebody is not related to herself or himself, then you're going to say it's not reflexive. But for symmetric, Elena is related to James. I have to make sure James is also related to Elena. But Austin is not related to Elena. Do I have to check whether Elena is related to Austin? No, you don't have to worry about that. So in that case, what do we need to check? You only check if you have EJ, you must have JE when you switch. If I don't have AE there, I don't have to have EA there either. If I'm going to make a small change to this example, suppose I'm going to change, say, Elena's age to 22. If I change that to 22, Will Elena still be related to James? Not anymore, right? So you're not going to have this, you're not going to have that anymore. You're only going to have 1, 2, 3, 4, 5. Still going to be reflexive, but will this be considered as symmetric? So notice that I just changed Elena's age from 19 to 22. So pretty much everybody has a different age. You're not going to have Elena related to James or James related to Elena. These two should be crossed out. So you're going to have would be those 5. And now the question is, will this age relation still be considered as symmetric? Yes or no? Yeah, you may, some students said, well, A is not related to E. Okay, well, you don't have to have that, okay? Because the definition says if X first person is related to second person, if you have that condition, then you must have second related to the first. But if you don't have AE, you don't have to have EA either, okay? So if you don't have any of them, this will still be symmetric because pretty much symmetric property automatically is true because you don't have any two different people related. You don't have to check anything. So that will still be considered as symmetric. Okay, just like the marriage relation we discussed. Apparently, if you married to somebody else, and then somebody else must be married to you. But it is possible that all the people we're discussing, for example, we have these 5 students here. Neither of them is married to the other in there, right? Okay, none of them is married to the other person. But it doesn't change the fact that marriage relation is symmetric, right? Just because nobody is married to the other person in here, it doesn't change the fact that marriage relation is symmetric. Because marriage relation, symmetric property says if, okay, so it's if Austin is married to somebody, that somebody must be married to him. But Austin is not married to anybody here, so I don't have to get the other conclusion to meet the other person is married to Austin. So just I want to clarify that. Now, any questions? All right. Now we're going to look at the last property, which is transitive property. It's sort of a little, maybe it's the most difficult one here. Now take a look. Reflexive, you and yourself, a number and itself. So there's only one number or one person involved when you check reflexive. Symmetric, X and Y, you usually have 2 different people, 2 different numbers. So there will be 2 people, 2 numbers involved. Transitive, it's going to be 3. 3 numbers with 3 people. So when we say a relation R is transitive, this is how we define it. For any 3 people with 3 numbers, X, Y, Z, from some set, if X is related to Y and Y is related to Z, then you must have X related to Z. So there are 3 people involved. First person, X related to the second person, Y. And the second person, Y, is also related to the third person, Z. You must have first person related to the third person. So the first and the third must be related. And let's check the age relation first. Okay. That's the definition. These are the 3 properties we have. So we're going to look at this example to explain that definition. Well, you have to have 3 people involved, right? So you're going to start with, let's say start with this one. Elena is related to James. I'm going to change it back to 19 as before. So Elena is related to James. James is related to Elena. So when I say 3 people involved, they don't have to be 3 different people. They could have 2 same people. So this is the first person, second person, and third person could be the same as the first. And third person could also be the same as the second. So in this case, first person, Elena related to James. James related to Elena. What do we have to check this time? You got to check whether the first is related to the third. So in this case, the first is Elena, the third is also Elena. Is Elena related to Elena? Yes, that's correct, right here. So in that case, but I only check the one. You do have to check every single one else. For example, if you consider this as first, this as second, and then that's going to be second and the third, I have to look backwards. First relate to second, second relate to the third. First has to relate to third. James is related to J, James related to James, which is also true. So technically, you're supposed to check every single one there, and it's a little tedious to do the transitive, check the transitive property because you may have a lot to check. So that's the idea. So this is transitive. Okay, now we are going to look at the two ones we did before. Let's start with the second one here. So is the second one less than relation transitive or not? So previously we determined it. The second relation is not reflexive because x cannot be less than x. It's not symmetric because even if we know x is less than y, we cannot guarantee y is less than x. But transitive property, that's to satisfy the transitive property. Think about the definition. So we have three numbers. We have x, y, z, three numbers. It says if x is related to y, in this case we use L, if x is related to y and y is related to z, can you prove x is related to z? Put a question mark here. If yes, then you say transitive. If not, you would say not transitive. Okay, so let's check. If x is related to y, what does it mean by x related to y in this relation? How is this relation defined? X is less than y, right? So I'm going to just put it right here. X is less than y. Now, how is y related to z defined? Y is less than z. Does everybody understand this? Y is less than z. Because the definition says a number is related to another second. A number is related to another number if the first is less than the second. Right? Okay, so it pretty much, what about, let's go ahead and figure out the last one. So what does x related to z mean? X is related to z, what does it mean by this relation? X is related to z by L relation. It means
X is less than Z.
yes, very good. Right? So now it becomes a question. What's the question? If x is less than y and y is less than z, can you guarantee x less than z?
Yes.
Yes, that's a common property. We actually used it right in the previous proof problem. So you would say yes. Okay, if it's yes, then okay, it's transitive. So although it's not reflexive, not symmetric, it is transitive. We know the less than relation is transitive, so you can x less than y, y less than z, and then x must be less than z. Okay, what about the first one? So in that case, again, usually I'm just going to write down the definition first. So this is the second example. I'm going to go back to do the first example. If you have trouble determining by looking at the definition, I'll suggest that you should always write down the definition first. Okay, so the definition says for any three numbers, if x is related to y and y related to z, then we have to check whether x is related to z, the first and the third, this one and the last one, the first one and last one. Now, then you have to figure out how x related to y is defined. In this case, x related to y means x minus y is even, right? So it's kind of like saying if x minus y is even and y related to z by the relation R, y related to z means y minus z is even. So let's write down y minus z is even. Now x, we need to check whether x is related to z. X related to z by relation R means x minus z is even. And that's also a very simple proof question. I think we kind of did this before. I think we did prove this when we do divisibility. So let me write down the whole question. It's not as obvious as the previous one. Say, if x is less than y, y is less than z, then we can tell, yes, x is less than z. You don't have to do any proof there. But for this one, you do have to do a quick proof here. So how do we prove if x minus y is even and y minus z is even, then x minus z is even? How do we prove that? Refresh your memories about the definition of even numbers again. So how do I describe an even number? Okay.
2 times an integer.
2 times an integer, so we can pick k here. Now y minus z is also even. I can write it as what? Y minus z is equal to, can I still use k? No, use a different letter, 2l maybe, because y minus z is even, but it may not be the same even number, so you cannot use k, just use a different letter. So it's 2l. Now, how do I get x minus z? You can do substitution, or you can simply add them. So let me move this second equation down here, so line them up like this, and do a addition. I can add the left-hand sides. What do we get after I add the left-hand side? Minus z, positive z, they cancel. I end up with, what do I get on the left?
Z.
X minus z, yes, exactly. So you're going to get x minus z right here. And 2k plus 2l, you can factor out a 2, k plus l. So look, what is x minus z? It's 2 times some integer, which tells us x minus z is even. So it's a very quick proof. And we did prove this before. If you know 2 numbers are even, when you add them, it's going to be even, right? Do you remember that was the first proof lesson we did? When you add 2 even numbers, the sum of 2 even numbers is still even. So we did do that before. If you say, well, that's the property we proved before, and you can just say the even number plus even number is still even, without doing all the definition, because we did do that before. So, okay, so we determined that this relation is also transitive. We also checked it's symmetric. Also. Okay. Now let's go back to look at the marriage relation and the major relation about transitive. Is marriage relation transitive? Yes or no? It's a little tricky. If the first person is married to the second person, but let's look at the definition while we're checking this. So, transitive. If x is married to y and y is married to z, can you say x is married to z? This is a little complicated because I guess it depends on which society you live in, because usually, I guess, for most of us, one person can only marry to another person, right? I mean, there are countries or places that maybe you can have 2 wives or 2 husbands. In that case, it will be different. So if we just consider one person can only marry to another person, you cannot marry to multiple people. In that case, the marriage relation will be considered what? Not transitive? Will be transitive because you don't even have X married to Y. Y has to be married to X. So this second person, third person has to be the same as X. Because it cannot be a third person, right? Because if we consider one person can only be married to another person, cannot be married to multiple people, then think about it. So let's look. So X is married to Y. And Y, who can Y be married to? Must be X, right? It cannot be a third person if we don't allow that. And I know maybe there are some places, yes, they can marry to two husbands, two wives, but let's not consider that. And in that case, do we have the first, I'm sorry, I guess you are right. Okay. So it's not transitive. Do you have X is married to Y? I'm sorry, X married to X?
No.
No, right? Okay, so you're right, it's not transitive. The marriage relation is not transitive. Because you cannot say a person is married to himself or herself. Okay, so that would be, not transitive. And what about a major relation? This one is not transitive. A marriage relation. What about major? Is that transitive? Yes or no? Yes.
Yeah.
That's right. Very good. So does everybody agree? If X has the same major as Y, Y has the same major as Z, then X must have the same major as Z, right? So that's transitive. Okay. So it looks like this one, the major relation is not only reflexive but also symmetric and transitive. So when you have a property that satisfies all three conditions, we have a name for this. We call it equivalence relation. And equivalence relation has very good a lot of good properties about equivalence relation. So we're going to discuss this probably later, maybe next Monday. The next section, section 3. So here, I'm just going to give you the name. So if you have a property which satisfies all three properties, a relation satisfies all three properties, we call this relation equivalence relation. Another quick example to check. Think about the friends relation. So if I define X is related to Y, if X is a friend of Y. For the first property, reflexive is a little, I guess, not well defined because you have to consider, do you consider you as a friend of yourself? I guess you can maybe I can say knows instead of a friend. Maybe I would say, what do we mean by friend if X knows Y? I'll just define this way, so that would be it will not be ambiguous. So when I say friends, I mean X knows Y well. And maybe just put X knows Y well. Maybe it's not the definition in social studies, but let's just make it easy that way. So take a look at this one. Is this reflexive?
Yeah.
Yes, right? You will consider, remember, so here, go over the three definitions again one more time. When you check reflexive, only one person is involved. You and yourself, X and X-self. So you will consider X is a friend of X, right? Because, like I said, a friend, I define X knows X well. So we assume you know yourself well. So it is reflexive. Second one, symmetric. But I can put a sentence here, X, because X is a friend of X. For anybody, any X, any person X. Now what about symmetric? Is this relation symmetric? Symmetric, you got to pick two people. Under the condition that X is a friend of Y, can you conclude, can you guarantee, switch them?
Yes.
Y is a friend of X. Yes, usually friends are mutual, right? I mean, it doesn't, I guess sometimes my daughter my 6-year-old daughter say, oh, so and so are my friends, but maybe they don't consider her as a friend. It's possible, but that's not, I think in that case, just say, okay, we mutually agree that, we're friends. So usually, normally, just by normal definition, if X is a friend of Y, but usually, then Y is a friend of X. What about the transitive property? Yes or no? No. Okay, think about it. Why not? Not transitive? Because when you have the condition, X is a friend of Y and Y is a friend of X. Remember, 3 people are involved. X is a friend of Y, Y is a friend of X. Can you guarantee the first person X is also a friend of this third person Z? You can't guarantee that, right? Okay, you haven't. Say, Elena is a friend of James, but James is a friend of Austin, but it doesn't mean Elena and Austin will know each other. Okay, so that would be not transitive because X is a friend of Y, and Y is a friend of X. That's given. So when you check symmetric or transitive, you already have some given conditions. Symmetric, you already know X is a friend of Y. You just have to check whether Y is a friend of X. And for transitive, you already know 2 conditions. X is a friend of Y, Y is a friend of Z. Does not guarantee Y is a friend of Z. So that would be not transitive. That example is kind of helps you to go over the difference between them. So now when we do I guess a lot of times in real life cases might be a little easier for us to think. But the homework questions, most of them, we don't have a real life situation for you, so it would just be like numbers. So we have a little bit of time to look at some of the questions here. So there will be 2 types of relations given. One of them is the relation is listed. So I'll tell you very clearly. So for example, the first problem that I gave you, the age relation, I did give you both ways. Well, so in this example, age relation, that's one way to define relation. So I'm not going to list everything. I just tell you, okay, how I'm going to define 2 people are related. If X has the same age as Y, that's how I define the relation. But you won't be able to see who is related to who. You don't know. You have to figure out yourself. The other way is I don't give you that. I'm just going to see, this is the relation I give you. So you can see very clearly. Austin related to Austin, Elena related to Elena related to James, and you can see every single one very clearly. So there are always 2 ways. But when you do these 2 types, the way you do it will be a little slightly different. So I'm going to try to see if I can give you one example of each. The first one will be like that. It's a pretty related pair is given. So we can look at example 10.2.1 on page 585. This is section, if you have different versions, it's under the relation. The second section under relations. May have different chapter number. Under relation, second section, it's called those 3 properties. So, example 10.2.1. So here is the set A given 0, 1, 2, 3. And we define those following relations. We have 3 relations defined. Define R as 0, 0, which means 0 is related to 0, 0 is related to 1, 0 is related to 3, 1 is related to 0, 1 is related to 1, 2 is related to 2, 3 is related to 0, and 3 is related to 3. So that's the first relation defined. As you can see, every related pair is given, so we don't have to do that ourselves. The second relation is also given as with. And third relation. Now we're going to determine about those three properties, whether each one is reflexive, transitive, or symmetric. Okay, so look at the first one. R. Is R reflexive? How did you know that? Yes, so because 0, 0 is in there, 0 is related to 0, 1 is related to 1, 2 is related to 2, 3 is related to 3. So you need to make sure every element, every number is related to itself. So 0, 1, 2, 3, I checked every single one. Yes, they are all related to itself. So it is reflexive. Now what about a second? Let's go ahead and just check all reflexive. So S. So is S reflexive? Is the relation S reflexive?
No,
No, why not?
because every element in A is not related to itself.
Some elements of A is not related to itself, right? 0, 0, for the first element, it is related to itself, but we don't have the second element. 1 is not related to 1, 2 is not related to 2, 3 is not related to 3. So we're missing a bunch. That's why we say it's not reflexive. So if you want to explain, you can just give me one example would be good. 1, because 1 is not related to 1. You can put a 1 common 1, so this pair is not in there, or you can put a 1 not related to 1, so in a way it's fine. So remember, in order to be reflexive, every number has to be related to itself. You have to have 0, 0, 1, 1, 2, 2, 3, 3. If you're missing any of them, not reflexive. So the third one, apparently it's not reflexive, right? It's for the same reason. Actually, for the last one, none of them is in there. We don't even have any of them. For the second one, we have 1, but we're still missing 3 of them. Okay, any question about reflexive? Now, next one, we're going to look at the symmetric. Go back to R. Is this symmetric? Yes, what did we have to check? 0, 1 is in here. So if you see 0, 1, so normally when you check symmetric, you check two different ones. So usually 0, 1 is here. You have to guarantee 1, 0 is in here, right? So do I have 1, 0? Yes, it's right here. 1, 0 is here. And we have a 0, 3. Do we have 3, 0? Yes, 3, 0. That's it. I don't have anything else to check, right? So this one and that one, they are a guarantee. And these two together guarantees the symmetric property. For example, if you say 1, 2 is not in here, it doesn't matter. We don't care. If 1, 2 is not here, as we don't have to have 2, 1, okay? As long as 2, 1 is not here, I don't need 1, 2 to be here. So you only need to check the one they have. If they have 0, 1, you must have 1, 0. So this one is symmetric. Now, what about S? Not symmetric. Explanation. How do you explain that? It's not symmetric. Yes. 0, 2 is in here, but I don't see a 2, 0. When you switch then it's not in here, then it makes it not symmetric. Similarly, if you say, well, 0, 3 is here, 3, 0 is not there, 2, 3 is here, 3, 2 is not there. That's right. Well, when you explain, when you give explanation, just one will do. So you don't have to say every single one. Because if one of them fails, it's not going to be symmetric. Last one will be the same, right? So 0, 1 is here, you don't have 1, 0, so it's not not symmetric either. Transitive is the difficult one to determine because you have to have check three numbers, which are two pairs. So take a look at the first one. You can determine. Okay. All right. So the tip is usually if they are equal, you can skip that checking that. It will guarantee it works. So when you check, just gonna check the different ones if they are the two numbers different. So I'm gonna start with this. I think of this as my first number. This is my second number. So 0 is related to 1. I'm gonna try to find does the second number 1 relate to something else? Is 1 related to any other number? Search here. I do find 1, right? 1 is related to 0. So this is the second, related to the third. And do we have the first related to the third? 0 is 0 related to 0? Yes, it's right there. So, okay, this pair is good. And you do have to check whether you can find other ones. Say 0, first, second number 1. Do we have the second number 1 is related to anything else? We do find another one, but like I said, the tip for you is you don't have to check that. You can check that. It will guarantee it works. So if you think of this as the second number, this is at third. Second and third are the same. Of course, the first is going to be related to third because the second and third is the same. It's already there. So if 0 related to 1, 1 related to 1, first number 0 definitely is going to relate to the third number 1 because it's the same as the second. It's already in there. So that's the tip that I gave you. When you check transitive, you don't have to check the ones with the same numbers. So pretty much, okay, so we're done with checking on that. But you still have to check 0, 3. So I checked this, I marked them out, and I'm going to check 0, 3. First number 0, second number 3. Do we have 3 related to another number? Different number? Yeah. Right here, right? So 0 related to 3, 3 related to 0, first related to third, 0 related to 0. It is true. So I verified this one also works. Maybe I should put check mark so it works. And again, you don't have to check 3, 3. Now check 1, 0. 1 is related to 0. Do I have 0 related to a different number? Right here, right? 0 related to 1. So that means the first number 1 has to relate to the third number 1. By the way, let me put this down here. I already marked it there, so it might be hard for you to see. So I'm working on this pair. 1 is related to 0. I found that the second number 0 is related to 1. So there's another pair, 0 related to 1. I kind of switched them for us to see. So first related to the second related to the third. Do we have 1 related to 1? First related to the third? Is 1 in there? Yes, right? So that one also works. And the last one we have to check is 3, 0. So 3 is related to 0. Do we have 0 related to something else? We found 1, 0 related to 1. Now, do you have 3 related to 1? Do we have 3, 1 in there? Unfortunately, 3, 1 is not in there. Here, it violates the third rule, so it's not transitive. So that's one thing. Transitive is a little tedious. You have to check every single one. It's not very easy to see. So what's the explanation for that? The explanation for this to be not transitive is since 3 is related to 0, and 0 is also related to 1. See, 3 related to 0, 0 related to 1. But we found out that 3 is not related to 1, not in here, not in the relation. So it's not transitive. Okay, all right, questions? Okay, all right. The next example, S. When you have many elements, it does take a little bit of time to check. This S and T should be quicker, much quicker. So when you check transitive. Pick a different one. So you can skip a 0, 0. So let's check 0, 2. Do I have, can I continue from 2? Is 2 related to something else? Right here, right? So 0 related to 2 related to 3. Do you have 0 related to 3? Yes. This one is good. Now let's look at the next pair. 0 is related to 3. But do I have 3 related to something else?
No.
No. So this one is good, automatically considered good because you cannot continue from there. That's the confusing part there. For transitive property, you must have those first 2, x related to y and y related to z. If you only have x related to y, but y is not related to anything else, this will be considered automatically true. You're not going to check anything else, okay? All right, so, well, that's good. 2 is related to 3. Is 3 related to anything else? No, right? So that one is good. So this will be considered as transitive. Any question about this? Again, that's the difficult part, confusing part there. Because in the past, the student thought, okay, you must have something to continue. If you don't have something to continue, you don't need to check whether the first related to the third. So similarly, the same thing here. This will be the third one will be transitive because you don't have 2 pairs that are related. See, 0 related to 1, but 1 is not related to anything else. So automatically will be considered as transitive. 2 related to 3. 3 is not related to anything else. So it's going to be transitive. Okay? All right. Well, I guess I don't really, I have 2 minutes I may be able to give you. I don't have time to give you an example for, another example for the, what if the relation is not listed in there? You may just be given something like that. You are only giving a definition, not listing. So I don't have time for that, but I can talk about something else. There's another thing that we can use to, like I said, checking transitive is really tedious, right? So we may be able to do it by graphing. So for every member here, we have 3 numbers, 0, 1, 2, 3. So I'm going to just put a 0, 1, 2, 3, like that. Put a dot for each one. If they're related, I'm going to draw a line to join them. So for example, I'm going to do maybe S. Well, I can't. 0 is related to 0, so I'm going to draw that. 0 is related to, because really, 0 is related to 2, I'm going to draw a arrow pointing to 2. 0 related to 2. 0 is related to 3, so I'm going to do that. 2 is related to 2, I'm going to do that. So you're going to get a graph, and by looking at the graph and determine those properties. I don't have time to...
Your meeting has ended.